Hello and good morning, everyone, and welcome to the Cyanobacteria What You Need to Know webinar. My name is Amy Smagula, and I'm going to be serving as moderator for the webinar. This is the second in a two-part webinar, which is offered by the New England chapter of the North American Lake Management Society. So if you would like to know more about the New England chapter of NOMS, we encourage you to become a member and support our efforts. We are a group of a variety of different individuals working with lakes across the region. If you are interested in becoming a member, you can go to the website that's shown here, or you could simply join us by sending your contact information and a check for $10 to our office in Rhode Island. A little bit more about who we are. The New England chapter is an affiliate of the North American Lake Management Society. And as our name implies, we are comprised of members from all of the different New England states. Our membership does include both lake and watershed residents, lake association members, various professionals dealing with topics in the field for lake and watershed management, students, academics, agency personnel, and more. And we have recently started doing online webinars instead of in-person meetings, even before the pandemic began, so that we could reach a broader audience and share more information with individuals. So our NECNOMS website is located down at the bottom right of this slide. And then to learn more about our parent organization, the North American Lake Management Society, please visit the link that's at the bottom below, and you can learn more about this group, which is, it has international membership. It's not just the North American Lake Management Society. We do have members from a number of different continents and countries. So if you missed the part one portion of our webinar, you can view it on one of the two websites that I just showed you, either the NECNOMS website or the NOMS website. That was held back on April 20th, and it looked at the topics of cyanobacteria in general, as well as their toxicity. Today, we're going to talk about cyanobacteria monitoring and control. A little bit more about this webinar. We are going to go from 10:30 a.m. to 12 o'clock p.m. Eastern Time. There will be two roughly 30-minute presentations, and there will be plenty of time at the end for questions. All attendees are muted. You will not be sharing your webcam, so even if it's on, we are not able to see it. And then if you have questions, please use the question dialog box to pose your questions. And then after the two presenters have given their talks, I will read off the questions and they will answer them. The webinar is being recorded and it will be shared off a link off either the NECNOMS or NOMS websites in a couple of days following the conclusion of this webinar. The two presentations for today are from Mr. Hilary Snook from US EPA Region 1. Hilary is going to be talking about monitoring approach to identifying and quantifying cyanobacteria in fresh water. And then our second presentation is by Dr. Ken Wagner with Water Resource Services, and he is going to be talking about control of cyanobacteria. And just a little bit about each of our presenters. Hilary Snook is a senior scientist for U.S. Environmental Protection Agency's New England Regional Laboratory. He holds a Bachelor of Science from Montana State University and a master's degree in civil and environmental engineering from Tufts University. His work involves the coordination and management of water quality and aquatic biological monitoring surveys for the region, and he provides a supporting role for national aquatic resource surveys presently being initiated by EPA. He has implemented ecological assessments of condition for wadable streams, large rivers, lakes and ponds, and near coastal waters for the past 25 years. So Hilary has a broad range of experience with different resources. And then Dr. Ken Wagner holds degrees from Dartmouth College and Cornell University, with his PhD earned in natural resource management in 1985. He has over 40 years of very diverse experience working on a variety of water resources, doing assessments and management projects, including lake, reservoir, river, watershed assessment, rehabilitation, and management. He's also worked with regulatory processes and educational programs. In 2010, Ken started Water Resource Services, a small company with a focus on water supply protection and lake management consulting. Ken is a former president of the North American Lake Management Society and former editor-in-chief of Lake and Reservoir Management, a peer-reviewed journal. So with those introductions of our two speakers, I am going to turn the presentation over to Hillary Snook, who will be presenting first. And we'll just take a moment in transition. And we have your slides, Hillary.
Okay, so we're good to go?
Yes.
Great. Thank you, Amy, and hello, everyone. Thank you for the opportunity to present today. It's great to be presenting for NECNOMS here and on a topic that I think is a lot of interest to everyone. So as Amy mentioned, this talk is about a monitoring approach to identify and quantify cyanobacteria in fresh water. It's mainly geared towards folks that maybe are new to cyanobacteria, haven't really been too involved in a monitoring program. So it's basically going to state why we monitor, what, when, where's, and how's. I'll show some tools that we use in the monitoring approach, and then a couple slides on quality assurance, some examples of what I think are great programs within the region, and a slide on toxicity, and then a little pitch on an opportunity that's presenting itself through EPA, at least for this summer and hopefully the next few years. So with that, I'll start out by saying that cyanobacteria blooms and toxins are here to stay. They've been around. If you caught Barry's presentation a month ago, they've been around for 3.5 billion years and are here at the present day. We also noticed that the toxins have had impacts in the more recent geologic past, 65 million years ago during the Jurassic period. We have evidence of massive die-offs around watering holes in northwest Madagascar, where we've seen the cyanobacteria in the fossilized records. In the more recent past, there's smoking gun evidence that the toxins are still wreaking havoc in certain areas. In May and June of 2020 in Botswana, we had a massive elephant die-off of approximately 300 animals around watering holes. There's still some controversy over whether the deaths were actually caused by toxic cyanobacteria or not, because many of the other animals were not affected around these watering holes, but the elephants were. And some of the autopsies showed extreme neurotoxicity or death from neurotoxins. So I'll mention this again, which will become an important point later in the presentation. But basically what this alludes to is the fact that as climate changes around us and we see more prevalence of cyanobacteria blooms occurring across the globe, we really need to start paying more attention, focus more efforts, and focus our monitoring on cyanobacteria and its effects. So we monitor cyanobacteria for many different reasons, depending on what agency you might represent or where your interests lie, potentially as a stakeholder. Public health departments, their monitoring is targeted on usually event-driven reasons. There is a recent dog death or the bloom occurrence that occurs within their jurisdiction. They will go out and investigate, potentially collect samples to send off for toxicity or cell counts and make a management decision on the resource at that point. So that's a very specific objective of their monitoring efforts. Public water supplies are legislatively mandated to monitor on a regular basis, very stringently in many cases. Their operational monitoring is usually continuous surveillance to make sure they don't have contaminants or toxins entering into their public supply stream. State, federal regulatory programs, research entities like researchers have different focuses. States monitor lakes on a regular basis seasonally. Feds such as myself will monitor on maybe specific survey programs like the National Lakes Assessment, which does a statistical probabilistic survey once every 5 years to get a snapshot of the resource condition across the country. And stakeholders such as yourself probably have a very different focus for an objective on why you might monitor, mainly because possibly you have a year-round residence on a water body, or you have a camp that you visit seasonally. Your objectives and reasons might be very different than some of these others. So the monitoring purpose is quite varied, and how you approach it is varied as well. So these are all bulleted lists of different things you need to take into consideration for your monitoring program. Probably one of the most important is that you do have a clear objective of what you're trying to accomplish through your system. And this can be a proactive or a reactive approach. Maybe you had a bloom that occurred over the recent past that hasn't ever occurred before in your water body, and you want to get a handle on what's going on. Or maybe you're taking a proactive approach where you've never seen a bloom or cyanobacteria in your system, but you want to understand what the vulnerability of your system might be in the future with changing conditions and landscape variables. So all these things, from funding to personnel to equipment, potential analytical costs incurred from sending samples out to a laboratory, what your experience and training needs are going to be for a program, when you are going to monitor, the size and logistics that are incurred with water body size are important, and what the sustainability of your program is going to be in the future are all considerations that you need to think about before you really get moving in your monitoring program. What we need to know, I think for any monitoring program, whether it's cyanobacteria or other, it's important to have critical baseline information. And this is just general information that might be collected once every 5 years or once every decade, or it might be collected on a seasonal basis. But this is kind of the skeletal architecture for any monitoring program. Watershed land use characteristics, the demographics and history. You know, is your water body just present day camps on septic, or has it been changed over to year-round housing and occupancy that may still be on septic, or have changed over to public municipal sewers? Has the landscape changed from agriculture to residential, or is it still predominantly ag? Those are all important things that will tell you a lot about what's happening within your water body itself. Hydrology, I think, is something that is somewhat overlooked often, or not looked at very closely, and is extremely important. How does groundwater impact your system? What's the rate of inflows and outflows through your lake? Is it a kettle hole lake where you're just getting groundwater influx into the system, which is the only addition of water other than precipitation events to it? Do you have a dam structure, control structure on your system? Physical chemical chemistry. This is really the fundamentals of monitoring these parameters. Wet chemistry is also included often when you're looking at problems within your system from harmful algal blooms or cyanobacteria blooms, mainly phosphorus and nitrogen. And then bathymetry, which might be a one-shot deal within your system to understand the morphology of your lake basin, can be an important factor in how blooms affect your system. And then specifically for cyanobacteria, you're adding another level to your baseline information where you're concerned about possibly looking at the composition within your system. Do you have toxin producers that are there? What is the percent dominance of a certain species? Do they, is it a single species that is showing up, or is it a combination? And with that combination, are there main toxin producers or not? Do you have the presence of picocyanobacteria, those less than 2 microns in size that can make up a predominance within a system? Or may it be a very clear lake system that you have, and you have benthic cyanobacteria mats that are present on the bottom of your lake. So these are all things you need to think about and how you target your program. What you're going to monitor within cyanobacteria, are you going to look at biovolume cell counts, which might require analytical expertise in a laboratory, along with cyanotoxins. Again, this adds expense to your cost, but it's important information. And depending on how your budget is, you may want to go to higher level monitoring with more research levels involved, where you're looking at zooplankton communities and how they affect the phytoplankton community and planktivorous fisheries within the system or other parameters. So it's complex. One size does not fit all. And you really have to target how you're going to spend your money and resources to get the best information out of it. So when should we sample? The objectives usually determines the when, in my mind, and this can vary from once a season or event-driven to daily and weekly levels of monitoring. And not every parameter that you monitor is going to be done at the same temporal frequency. But I will say that frequency and duration really determines the resolution. Some things you don't need high resolution to meet your objective, and others do. So some examples here of layers of information. This top graphic shows the progression of dissolved oxygen through the water column through the course of the seasons. This is over a weekly basis for an 11-month period. And you can see during the summer months, your oxygen is deprived in the bottom layer. We can transfer this information onto a plan view of graphic of how this anoxic layer expands through your water body through the course of the season. And from there, we get an inference of basically what area within the lake is available to have biota surviving and stressed. And we can also look at what this anoxic layer might be doing to the release of nutrients within the sediments to help propagate cyanobacteria blooms throughout the water column. So it can be a very useful tool looking at how it changes throughout the seasons and how we manage this water body and provide controls for it. Here's another example of how we might sample. This is probably something that's not going to be done at the lake level, but it shows the information you can get from different levels of resolution. This is a buoy that's put out with a multi-probe meter in the Charles River Basin down by the Museum of Science that puts information out to a kiosk within the museum at 15-minute intervals. And I just wanted to show here the important thing to look at, if you follow my cursor, is you're seeing these blips, this up and down movement of concentration throughout the course of the early summer season. This is showing the diurnal fluctuation or migration of cyanobacteria within the water column through the course of the early summer, through these 15-minute intervals. If you remember from Barry Rosen's presentation, the aerotopes within the bloom-forming cyanobacteria can be regulated so they can maximize sunlight availability on a diurnal basis. So you see that in the early summer. Then as it starts to warm up, we start to see cell division take place and the logarithmic growth of cyanobacteria. So we're still seeing diurnal migration take place, but we're also seeing the propagation of cyanobacteria biovolume as it occurs as well. So this can be a nice early warning system of when blooms may form when we start to see this growth curve start to take off. Where to sample is equally as important. Lakes with cyanobacteria are often very heterogeneous in nature. I use this heat map all the time. That was done by Amanda McQuaid when she's working, or a student at UNH. It shows fluorescence values translated to cells per milliliter, and you can see there's a high amount of variability within the system on this particular day. The World Health Organization uses a cell count threshold of 70,000 cells per mil for a guideline value for issuing advisories. A lot of states in New England use this as a threshold for posting advisories. So what's really important when you talk about where to sample is where you sample in this particular water body and will really give you a different perception of what the potential risk is. So if you're up in this upper northern corner here, and you might have a camp or a public beach, you take a sample on this given day, you're going to have a very different perception of risk than if you're sampling down in a different area where this blue is. So where to sample is important depending on your objectives, points of contact, critical exposure points of where people or pets might be subjected to cyanobacteria blooms is something to take into consideration. If you're looking at trends through the season, you might want to have an index site similar to something like the Charles River, where it's a fixed point in time that you track through the course of the season. So you might want to have a point of contact, or you might want to do lake-wide monitoring. Those are going to be different objectives and require different monitoring approaches. Another example is a windward shoreline, where you might be interested in looking at prevailing winds during the course of the season when blooms occur. Maybe another different monitoring strategy as an example. So not only do we have horizontal heterogeneity within a lake system, we also have vertical heterogeneity that takes place. It can be very patchy throughout the water column, cyanobacteria blooms, but also you can have cyanobacteria blooms that occur that you never see, that are occurring right on this thermocline or metalimnetic layer, where they will just lay there on top of that density gradient within the system. And so you may have a bloom occurring that you don't see. And if you're a recreator on the top, on the surface, of the water column, it may not be a big issue at all. But if you're a drinking water supplier, as Barry's earlier talk alluded to, and you're pulling water down from this area, that could be a very significant and very important place to monitor. So location is extremely important. These guys are interesting because the bacteria or cyanobacteria that usually spend their time down here are able to capture light at longer wavelength frequencies. So the blue and green wavelengths of light penetrate deeper in the water column. These guys don't have to move. They're perfectly content to stay down here and capture these longer wavelengths of light to function, where other bloom-forming cyanobacteria have to utilize these shorter wavelengths and be further up in the water column. So where to sample, again, is extremely important. If we go back to that slide, if you remember that I showed of the elephant deaths in Botswana, one of the thoughts is that elephants drink water very differently than the other animals in the area that drink. The other animals drink off the surface, but elephants will go deep into the watering hole and actually pull water off the bottom. So they might be, one of the thoughts is that they're pulling some of these potent toxins that might be just in a very discrete layer near the bottom where the sediment water interface at the bottom of these pools. So jury's still out on that, but it's an interesting theory. So how do I sample? Again, lots of different ways to sample. A lot of people are familiar with this, but we have grab samples off the surface. We can do integrated tubes, which are collecting a sample, integrating it throughout the photic zone through the water column. Each one is going to require different objectives and different perspectives and considerations. For example, if we look at something as simple as a grab sample, we're grabbing a sample right off the surface. We can have a high degree of variability if we're looking at cell counts, depending on how we grab the sample right off of the surface. Orders of magnitude difference, just in a simple few inches of where that sample is collected. And if we're doing toxin analysis using grab samples, that can be very important as well. Certain toxins adhere to the plastics of the sample, so we might underestimate what the toxicity of a water body is if we use the wrong container. Certain containers rely on clear glass, others have to use amber glass because they're subjected to degradation through sunlight. So sample containers are very important, as well as how we sample. Another type that we use is called an integrated or a discrete sampler. This is a Van Dorn sampler, which we can lower to a depth. In the last slide, where we look at that bloom occurring right in the metalimnion, we can go down to that depth, use this sampler, drop it down to that depth in the water column, trigger these cups to close with a certain messenger that we sent down, and we capture a sample of water right from that and cyanobacteria right from that discrete depth, which can be very important for certain objectives. Other probes that we use or other tools are these multi-parameter probes. These can be modestly expensive to extremely expensive. The ones we use in the lab at EPA that are newer versions, they're all optical probes for DO, pH, temperature, conductivity, and cyanobacteria pigments. These can run upwards of $20,000 per unit, so pretty expensive for most folks to use. But there are other options out there. We can get DO meters for around $1,200 and temperature loggers, things that you actually deploy and leave out. Some states are leaving it out on a year-round basis and kind of daisy chaining them through the water column, and then collecting that information based on preset intervals. It can be continuous to daily to pretty much whatever you want to set it for, and then you retrieve it and download the data later. So a useful tool. Plankton nets I don't have a picture of here, but if you're looking at phytoplankton community, you want to get a semi-quantitative to quantitative assessment of what you have in the system, you can do that using that tool. It does not collect picocyanobacteria though, because these mesh size of these nets are about 50 microns, and picos go right through them at 2 microns and less in size, very, very tiny. So all these monitoring conditions and sampling, you also need to take into consideration, are we doing composited samples, averaging, collecting multiple samples at different locations, putting them together and getting an average of condition, or are we doing integrated samples vertically through the water column, maybe compositing several of those versus discrete samples. So the main point of this slide is really there's lots of variables there, and you really have to focus on what your objective is going to be, along with all your costs and levels of expertise and other considerations. So quantifying cyanobacteria, this can vary considerably as well. If you have kind of a tin cup budget, it can be as simple as getting a glass jar, filling it with your observed water and letting it sit. This is called the jar and stick test. If you sample and it sinks to the bottom, this is more than likely not going to be any cyanobacteria. If you have it floating to the surface and forming a scum up on the surface, that is most definitely going to be cyanobacteria, bloom-forming cyanobacteria that has the aerotopes and buoyancy that's going to bring them to the surface. There are exceptions to every rule. You can get some cyanos that are more benthic mat forms that can adhere to a stick, but in most cases, cyanobacteria is not going to form these mats like this and be able to be picked up with a stick. So that's a real simple, like I said, the tin cup bare bones monitoring. You can go to another up to different levels, such as looking at samples under a microscope to see if you just have toxic genera that are present. And there's different gradations of this, moving up into hiring out a lab to look at percent composition and dominance, to look at what species you have, what the dominant species is, and is it a toxin producer, looking at cell counts, which most of the state agencies use for threshold levels that may trigger toxins and be used for advisories. Then you can get into toxin analysis, which simple ELISA tests to more complex PCR analysis. Other surrogates for cyanobacteria can be chlorophyll A sampling, which can correlate quite well to cyanobacteria, as well as Secchi disc readings and fluorescence of those glycobilly proteins that you see in cyanobacteria that Barry had talked about in the earlier presentation. So I will spend a minute to talk about fluorescence, because this is a tool that we use quite a bit in the region. It's quite reliable, it's quite good. It's an inexpensive tool that can be used. And also you get data pretty quickly. You aren't sending samples out for a week for toxin analysis or cell counts. This is something you can do on site within a matter of hours. So basically what this instrument does is you collect the water sample, process it a little bit, and you're gonna subject it to a light of a specific wavelength, and it will absorb this light, a specific wavelength that it uses to function, and then it will emit light at a different wavelength, and we can read that for this particular pigment, which is exclusive to cyanobacteria, called phycocyanin, and we can read this through our instrument, and we get a direct relationship between actually the pigment fluorescence and the cell concentration within the water body system. So here's an example from the World Health Organization, which shows how fluorescence can track with cell counts. It tracks very closely. So if you're looking at wanting to track a system and maybe forecast a little bit when a bloom might occur, you can use this on a daily basis and track when you start to see that logarithmic growth phase later in the season, when blooms likely occur, and get a kind of a pre-warning of when you might have problems within your system, or you might have potential for points of contact exposure, which might have toxins associated with them. So a very useful tool, reasonable price point for it. That can be very useful for monitoring programs. So note on quality assurance as well. This is something that is often overlooked in programs. And I state here that no amount of precise analytical work is going to compensate for poorly executed sampling. You can add a high level of variability and stuff by poor sampling protocols and methodology. So you really want to be aware of that and make sure that it's well executed. Because inconsistent sampling is going to have inconsistent data that's not going to tell you that much. Oftentimes samples I get in the lab, it's kind of interesting that this is not infrequent where I will get samples in that people have taken the care to ship into me, but I can't read the labels. They've used ink that kind of dissolves in water. The labels are washed off. Maybe they have a sampling date, but they don't have a sampling time. I can't read the contact person's name on it. So it can be pretty problematic. So take the time to do that well and thoroughly. Monitoring can be costly. It takes a lot of time and effort to collect those samples, and you want the data to reflect that. So just a note on quality assurance. A couple programs that I wanted to highlight here, just a couple of them that have been successful, and there's a lot of them within the region that I could remember. These are a couple that came to mind. One is more of a local grassroots organization through the Worcester Department of Public Works, the Worcester Cyanobacteria Monitoring Collaborative, which was started after the larger regional collaborative gave a little workshop and demo. They took off of this. Hats off to Jackie Burmeister for putting this together. They sample on a monthly basis. They give trainings to genus level microscopy work for identifying what they have in their systems. They put out newsletters on a monthly basis during the sampling season. And all this builds a lot of awareness and education and participation around the water bodies that they're sampling, and also is used by the Department of Public Works for managing these systems within the city of Worcester. This program has grown. They're now up to, over the past 4 years, have grown from doing 1 or 2 water bodies to up to about 13 in the greater Worcester area. And like I said, they put out these monthly reports during the bloom season, which are really informative to folks. Great outreach program, a great program for the Public Works Department. Another program that is quite successful that was developed in Vermont, spearheaded by Angela Shambaugh from the Vermont Department of Environmental Conservation in collaboration with the Department of Public Health, is their Cyanobacteria program, where they have an alert system, where they have volunteers that are trained annually and do weekly reporting around Lake Champlain at fixed monitoring points. Basically, it's a visual assessment, giving different alert levels. And when they get to the high alert level or maybe low alert level, they will actually go out, collect samples, look at them microscopically to see what they have within the system, and send those samples off, collect samples to send off to the Department of Public Health for toxin analysis. Great program for Lake Champlain. It's been going strong. It's put out in a weekly report online. On a given year, we should see all kinds of different points here showing these different alert levels, generally safe to low and high alert levels. But due to COVID last year, they didn't sample. And this year they haven't started up yet. So when I went online to look for the dots and stuff to show up, they weren't there. But anyway, you can probably look this summer and you'll see how their program works. Very great program, doing well and highly successful. And they are starting to expand out, I think, to some of the lakes in Vermont as well, besides Lake Champlain. So, last program I'll mention is our own, which I'm a part of. It's the Cyanobacteria Monitoring Collaborative. It was started back around 2013 by concerns from state water quality agencies. We all got together, the state agencies, the feds, local lake associations, private businesses, and talked about how we could put a program together and really make it work for different levels of monitoring and different objectives. So there's 3 levels. It is a tiered system depending on your level of commitment. Bloom Watch is a phone app, which is developed for notification and surveillance based on the requests coming in from the states. The second level is Cyanoscope, which gives you more understanding and educational awareness of what's going on within your system, such as what the Worcester Collaborative is doing now. And then Cyano Monitoring, which is looking at a more deeper level understanding of your system and has a more temporal component to it. You're sampling at a much more frequent basis to get higher resolution of what's going on within your system. So cost, training experience, and commitment of time and effort increases as you go up in these tiers within the system. A little bit about the different tier levels. At the Bloom Watch level, the phone app that's out there, we have also built a dashboard which is available online, where when you take these images and submit them, not only does it will it notify your contacts that you have put into your phone app to be notified, but it will post the pictures of your blooms. It will give you some general statistics on what the conditions are, weather conditions, and the report out dates of when these blooms occurred. So we can track these blooms through the course of the season and where they occur. You can select up here by your state or region. We can use these tools here to actually draw like a lasso around this area and zoom in just on that particular points. And these graphics will change accordingly to the area that you're focused in on. So we are building this now. This is posted on our cyanos.org webpage. And we're also looking at hopefully developing this to be also included the dashboard in the phone app as well. Cyanoscope, that mid-level, we're using the microscope to look at genus level identifications of cyanobacteria. You can collect your samples, put them under the microscope, take these images and upload them to iNaturalists in the Cyanoscope project. And these will be verified and confirmed on as to the genus level identifications, so that we have, once it's been confirmed by other taxonomists, we'll give it a research grade notification to confirm that what you think it is indeed what it is for confirmation. These are geo-referenced, all these locations, and they're posted on the iNaturalist page. And as you can see, we're getting participation from around the globe, which makes it fun, makes it interesting, and we're sharing that experience and information. Again, this is the toolkit that's used for that mid-level and the Cyano monitoring upper level as well. Everything's here. This is available for purchase, or you can purchase component parts. We don't sell it through EPA, but we do have vendors that can get this for you. So note on testing for toxins, I just want to touch on this quickly because I think it's extremely important. I've had organizations come to me and say, hey, we've been testing for microcystin on a weekly basis just to make sure that we're okay. That might not be the best expenditure of your funding. You might want to spend it elsewhere and get more bang for your buck. And one of the reasons is things like some cyanobacteria, such as Dolichospermum, they don't just produce a single toxin. They have the potential of producing all these toxins. And so monitoring just for microcystin, doing a toxin analysis for microcystin, though it is the dominant toxin that seems to be out there, you might miss many of these other toxins. So you may not get the most bang for your buck on that. So that's the main point, and other cyanobacteria do the same thing. They are capable of producing different levels of toxins for it. So another note on toxicity, this guy, he was a Swiss alchemist from the Renaissance period named Philip Aurelius Theophrastus Bombastus von Hohenheim. I just like saying the name, but he shortened it to Paracelsus. But he came up with a concept that all things are poisonous, and it's all about the dose. And I think this is a very important take-home message for cyanobacteria monitoring and our perception of risk. So all things can be poisonous. Case in point, in 2007, there's a hyponatremia death of a young lady in California. Hyponatremia is death from the ingestion of drinking too much water. This is not an uncommon occurrence in animals such as dogs and cats. The case fatality rate for hyponatremia in dogs and cats is anywhere from 12 to 14%, which is not really that low. So that alludes to the fact that some of these reported deaths of dogs around water bodies may be due to hyponatremia rather than cyanobacteria toxins. Again, sometimes we don't have the evidence there to make a conclusive determination of what that death might be. So we really need a pragmatic approach to real versus perceived risks of cyanobacteria in these systems and how we approach it and manage our sources. So with that in mind, I'd like to just throw out a pitch a little bit from the Cyanobacteria Collaborative Program. We have a toxicity lab that is finally getting underway at EPA to do fluorescence work, some cell enumeration, identification, and toxicity testing. So for those that are interested in getting some tox analysis done, we are looking at welcoming samples into our laboratory as long as they're accompanied with bloom watch images that have geo-referenced and have images of where those blooms are and what those blooms look like. As Elizabeth mentioned in her talk earlier, toxin data is poorly associated with blooms. We don't have that connection. This is an opportunity to gather some of that data through georeferenced imagery and cyanotoxin analysis. So don't be alone there floating around in the universe as a entity unto yourself. Try to network with folks. Cyanobacteria takes a lot of expertise, from water quality managers, lake resource managers, to phycologists, to taxonomists, to water quality specialists, and so forth. And they all have something to offer. And as Aristotle has said, the whole is greater than the sum of its parts. So please take advantage of that. And with that, I will end my talk. Hopefully I didn't go over too much. Feel free to contact me if you're interested in any toxicity testing or anything else related to cyanobacteria for that matter, and visit the website, cyanos.org. So with that, I'll stop, and thank you very much. Hope I didn't go too far over.
No, that was great. Thanks so much, Hillary. All right, as we transition over to our second presenter, Dr. Ken Wagner, I just want to remind folks to please type your questions into the question box. I did see a couple questions come in. We're going to hold questions until the end, so you have plenty of time to get them in if you do have questions. All right, so it looks like Ken is ready to go, so I'm going to turn it over to him. Ken?
Okay, good morning. This is the last of 4 talks in a 2-part webinar. Dr. Barry Rosen explained to us about blue-green algae, their specialized structures and physiology that makes them such good competitors and why we have blooms. Dr. Elizabeth Hilmore explained to us about the toxins they produce and what threats they actually pose. And now you've had Hillary Snook explain to us quite a bit about how we might monitor to keep track of them. I get to handle the question that everybody is asking, how do I kill these things? Really, we're to prevent them from happening in the first place. So in a very short section here, I'm going to try to give you the rundown of everything that can be done with some relative sense of what works better than others. But all these tools have value. There's an ecological basis for control. This is a critically important piece to understand. Basically, algae blooms of any kind, cyanobacteria and otherwise, are a function of an imbalance between growth and loss processes. Growth is, the actual recruitment from the sediment, washing in from upstream, growth of individual cells, cell division, and so on. Loss is simply the death of the cells. So they may die physiologically, they may be consumed by zooplankton, they may be flushed out of the system, or we can kill them. But it's a matter of having algae in the system is completely natural. In fact, it's essential if you want to have zooplankton, small fish, big fish, and we catch the big fish. So for a functioning aquatic system, these are all important parts. What we don't want is bottlenecks where the biomass accumulates, particularly for algae and particularly for cyanobacteria. So all of our ecological basis for control feeds into our efforts to control these algae. We're either attacking growth or loss processes. Cyanobacteria are not all alike. We throw them together in a group just like we would with green algae or diatoms or dinoflagellates, and that's fine taxonomically. They are a very distinct group. However, they're not all the same. They have different toxins, as Hillary just explained and Elizabeth did last webinar. They have different structures that make them competitive that not all have. Barry explained that last webinar. So you have to know something about them, and you need to know particularly the mode of bloom formation. There's only three ways they form blooms. One is just organic growth, some get in the water column from wherever, and the conditions are favorable, and they grow into a bloom. We used to think that's how it all happened, and it turns out that's not all that common. Otherwise, we can have a meadow-medic, middle depth, you know, where if you have a stratified lake, where they can grow there, utilizing the nutrients from below and the light from above. I gather my sound isn't perfect, so we're going to make an adjustment here. That makes it any better.
There we go. Hopefully that makes the sound better. I might add, I'm coming to you from the site of the Cyanobacteria monitoring project at a lake in New Hampshire, and they're actually working out there on the lake right now. We'll go back and assist when we're done. So multitasking today. Anyway, the bloom mechanism that turns out to be probably the most important and most common for real problem blooms is growth on the bottom. Not so deep that there isn't light, but deep enough that you can get nutrients off the bottom as decomposition or release under low oxygen occurs. And those cyanobacteria suck up the nutrients and then rise to the top, sort of like packing a picnic lunch and going up to the top of the hill to enjoy the view. So you need to understand cyanobacteria ecology if you really want to understand control. Again, the first half of this whole webinar series was focused on that. And now the actual monitoring is essential to know what you're dealing with. And then we go into the control. All right, job one is always watershed management. It is true that you often can't get rid of the problem just by working in the watershed, but ultimately the problem came from the watershed. On the left there is actually a diagram of the phosphorus concentrations, natural background phosphorus concentrations in the Northeast. And you can see that the blue is the lowest and the yellowish or cream is the highest. So we have a range. You have to know where you are and what the logical background is going to be. Watershed management could be a course in its own right. In fact, I used to teach a course on that. It really boils down to two things. You either control the sources or you trap the nutrients before they can get to the lake. You can ban certain high impact actions. You can import or implement a whole bunch of best management practices that will limit the release. But ultimately, if you've got a substantial amount of urban or agricultural land in your watershed, nutrients are going to get off that land. They're going to get in the water and move down. So you need some form of pollutant trapping, detention, infiltration, some sort of form of uptake or treatment. Wetlands are a great example. Maintenance of facilities to minimize the problem. The problem is that developed land typically increases the loading by more than any best management practice can actually get rid of it. Again, agricultural impacts are just as bad, sometimes worse than urban impacts. And if there's more than about 20% of the watershed in some sort of developed use, you're likely to see an impact on water quality. I've seen some really nice references suggesting it could be as low as 6 to 10%. And I've seen a few where if you do a really good job, you can get away with maybe 30%. But the bottom line is you can't have an urban watershed like on the lower left picture there, the land on the upper right is never going to behave like the land on the lower left. And the analogy that I like to use is a leaky boat. If you have leaks in your boat and it fills up, so those poor folks on the right going for a ride, you can patch the leaks, but it's not going to get the water out of the boat. You've got to bail out or turn on the bilge pump or whatever. So there are in-lake and watershed management actions that are both essential to remediate an existing problem. Watershed management is what protects your lake and keeps it from getting the problem. Once you have the problem, you have to still fix the watershed, but you usually have to do something in the lake. All right, the data needs are pretty extensive. You don't have to know every last detail about every one of these, but you need to know a lot. And all these things are important to what will work and what the best choice would be. Okay, running right through the list. Okay, harvesting isn't something you do very often for this sort of thing. You certainly can't pick up typical planktonic cyanobacteria with them. You can modify those conveyor belts to be more of like a conveyor like you'd see in a supermarket, and you can pick up algal mats with it. So when you do get a cyanobacterium like Lingbia that will pop up from the bottom late in summer, particularly in more southern climates, but occasionally in New England, you could harvest them with those. But of course, now you've already got the problem. What I'm doing here is I'm focusing first on increasing the loss processes, by the way. All these things I'm going to tell you about now are basically increasing the loss of cyanobacteria. Okay, flushing. Flushing is a pretty useful technique if you have a substantial water supply. The picture on the bottom there is actually Moses Lake out in Washington, where they literally diverted part of the Columbia River through it. I mean, that's pretty neat, but you know, it's not something that you can do on a regular basis in most lakes, particularly in the summer where we have less water available to us. Even if you could use a public supply, bear in mind that under the Safe Drinking Water Act, a lot of water supplies in the distribution system are treated with phosphates to minimize corrosion of pipes. So you could literally have eutrophic drinking water. If you put that water in your lake, you're adding phosphorus. If you flush the lake, literally replacing the water about every 3 weeks, you probably prevent most algal blooms from developing just because it takes some time. You may still get stuff popping up off the bottom. And keep in mind that unless that water is literally distilled water, you're still adding nutrients to the system. You're increasing the load, you're just increasing the flushing. Okay, sonication. Again, this basically disrupts cell walls, often just causes the inner part to separate from the outer. It does not necessarily burst the cell. You will get a release of nutrients in many cases. It's not going to eliminate every type of algae that would be out there, but you could in fact make quite a difference for cyanobacteria, particularly those that have gas vacuoles in them, ones that are able to pop up off the bottom and become the floating scums and surface problems that we have. That can be dealt with sonication very well because it collapses those gas vesicles and makes them sink. So there is some real benefit there. The pictures on the bottom are typical product literature. It looks bad on the left and better on the right. You don't want to get to the point where you're on the left. You want to prevent the problem from happening in the first place. So you would have these out and turned on from about now in the year through the summer. And there's different ones out there. There's 2 primary manufacturers, and there's different arrays. You can have them pointing in all directions or just one direction. Just keep in mind, it's a line of sight technique. If the sound waves can't directly hit it, it won't work. So if you successfully clear the water in a shallow area, you might expect rooted plants to grow, and then they're going to block the technique. So there's some limitations there, but it's not snake oil. It has a real solid base in science and how it works, and it can in fact make a difference, particularly in smaller ponds or situations where you can't control the nutrients. Ugh, not liking what I'm doing here.
Don't leave webinar. Just click
There. Go ahead, we're getting some help here. That didn't work either. There we go. We can try it that way. Nothing like computer glitches. Algicides are a hot topic in many places. I know a lot of people don't like the idea of putting chemicals in the water. Treat this just like a medicine. Is it a medicine or a drug? There are reasons to take medicines for things. There's probably not a good reason to drug yourself up. There's a lot of nuances here, but there's relatively few ingredients out there. We have copper products and peroxide-based products that are by far the most common. There's a little bit of use of endothol and flumioxazin, which are actually normally thought of as plant herbicides, but they will impact some of the green algae mats, and same thing for Lingby and some of the blue-green mats. The effectiveness and longevity are important considerations. It doesn't always last that long. Copper gives you pretty rapid results. It does affect most cyanobacteria and does a pretty good job on them at very low doses in New England. There are a few resistant forms. You have to be careful of that. It can lyse the cells, releasing the contents in the water, which is an issue when toxins are present, which is why a lot of the states have standards for not allowing this sort of algicide use when the cell count is already too high. If the toxins aren't there, it shouldn't be a problem, but you need to test for that. The formulation affects the time in solution and the effectiveness, and there are a lot of formulations. It is not fair to just say I'm applying copper. The exact formulation matters. There is possible toxicity to other aquatic organisms. Used according to the label and the way it gets used in most New England states, this is very uncommon. It's not a big deal. You may hurt some zooplankton, which is not a good thing, but you're not going to kill fish most of the time. There can be a long-term buildup in sediment, but there's very little evidence that this has been a major negative impact. I think if you do enough of it, you're going to have trouble getting rid of the sediment if you ever dredge, but it's not an immediate toxicity problem once it's reacted. Usually it's applied to the surface. You can inject it deeper, and if these algae are growing at the bottom, you could use weighted hoses or a chilled solution and actually kill them in place without having copper distributed throughout your water column. That's a real benefit. Peroxide is sort of the same idea, except that it works best on thin-walled forms. It literally sort of dissolves the cell wall, and cyanobacteria are in that group, so it will be preferentially more effective on cyanobacteria than other algae that you might consider more beneficial. It degrades to non-toxic components, so it's good that way, and it may also oxidize some toxins, which is a plus. You also apply it to the surface, but you can get to a greater depth with some of the granular forms because they'll land on the bottom, and you don't have any accumulation of unwanted contaminants in the water or the sediment. It is more expensive than copper in general, but the dose and frequency of use have to be considered. In the long run, it may be completely workable. Use of algicides should be done early in bloom formation to prevent the problem from occurring. This is the problem. This is what gives algicides a bad eye. Somebody calls the applicators, my lake is green, you need to treat. It's not the right time. It may be what you have to do under the circumstances, but you need to be monitoring. Back to Hillary's talk. You need to know what's going on. This is a great example here in a place, South Pond. It's in Massachusetts. If you notice on the left side, my cursor shows up, but we've got the first copper treatment when the algae are starting to jump up above 3,000 micrograms per liter, and a little bit of blue-greens are showing up. We hit it, got through the rest of the year with no issues. The next year, we should have hit it right after this June 22nd date. We're starting to rise, and we had blue-greens, but they said, it's not that bad yet. We'll wait a couple weeks. Well, there's what they got, a cyanobacteria bloom with plenty of other stuff, and we did treat. It did work, but notice we had it back again with some problems later the same year. If you don't prevent the problem, you may have bigger problems down the road. The next year, well, that meant it did a second treatment there. The next year, they got it right again. They hit it as soon as the blue-green showed up, did fine. And this last year is actually an aluminum treatment, so it doesn't relate. So there are ways to do it right and ways not to do it right. You should be able to get away with an annual application. If you need more, you need to look for alternative approaches. Barley straw is one such approach. This is an unregistered algicide. Basically, the decay of the straw produces a fairly potent algicide that does affect blue-green algae pretty well. So there's a real potential there to have this work, but you've got to get it out there. It's got to get distributed. Technically, in most of New England, a registered or licensed herbicide applicator can't use this because it's not a licensed algicide. People do use it. There are success stories, but it's not terribly reliable. Reliable meaning you can't count on the results that you'll get every time. Oops, go back one. Well, I jumped by, but that's okay. It was about viral issues. Basically, there are no viral products available at this point. There was a burst of activity in them in the 70s, then again, the early 2000s. Bottom line is that you just go from really green to slightly green and it never wipes them out, and there's nothing available to you right now anyway. So it's not really a technique anybody's using these days. Biomanipulation is a really interesting one. I actually partly put myself through grad school doing projects like this. If you balance the fish community and you get more large zooplankton, and again, if you think that the one up here at the top left is a Daphnia, the filtering capacity of a zooplankton is related to the cube of its body length. So the one big one is worth all the other small ones in the picture plus some. You want lots of big zooplanktons. They will give you the least amount of algae for the amount of fertility you have. Now, if you have a lot of fertility, a lot of phosphorus, it's not going to work out too well. But if you're down in the 20 or 30 microgram per liter of phosphorus, and that's enough to cause algal blooms in New England, but you have a really good population of zooplankton with lots of big Daphnia and things like that, you'll often have clear enough water to get by. One of the problems is that cyanobacteria are particularly good at coming in as big chunks that are harder to eat. I think that's, yeah, the next one there. So there's a Daphnia in the upper left. At the same scale, there's Dolichospermum lermanii, yes, gesundheit. It's like giving Uri a 6-foot plate of spaghetti and no utensils. They just can't eat all this. So there's a real issue there in that you want to have big zooplanktons, and they will give you clearer water, but they're not usually the answer by themselves, particularly if you have cyanobacteria problems. It is true, though, that if you have a lot of Daphnia, and you can see here in this graphic that the further you go out to the right and the higher the Daphnia biomass, the greater the clarity, and that's all in meters on the left. One issue, and this is a hot topic in Maine right now, is they're trying to restore alewife runs to lakes that historically had them. And that's ecologically a really sound idea. It's great for the estuarine environment. I think it's good overall in the aquatic environment to restore linkages that we've messed up by putting in dams and things. The problem is those lakes are not the same as they were a couple hundred years ago when there was hardly any human settlement around them and not a lot of nutrients going into them. And now you put in the alewife, and of course you get no Daphnia, they wipe them out. That's what shows in this graph. And you wind up with lower clarity than you would have otherwise. Now the clarity doesn't have to be bad. These are all lakes that have been treated with aluminum, so they don't have a serious phosphorus problem. But the lowest is around 2 meters, not great. The highest is 6. But of course you can get much higher clarity if you've got more zooplankton, and to have more zooplankton, you really can't have alewife. Okay, in lake, this is now growth control, no longer loss. The first of the growth control things is just to use a part of your lake like the watershed and try to get the nutrients out. What you're looking at is a forebay put in a small lake in Massachusetts that captures runoff and treats it in sort of this wetlandy area. And they literally went from having 200 micrograms per liter of phosphorus out in the lake to 20 micrograms per liter. And that's not perfect, but it's a pretty major improvement. So you can do this, but of course you're basically taking a watershed function and putting it in your lake, and you got to lose some space to do it. Selective withdrawal is a fascinating one. That's been around for multiple decades. It doesn't get used a lot, but if you can let the deepest water be discharged from the lake instead of the shallowest water, you'll get rid of the poorest quality water. And in the long run, you can actually run those reserves out. I have seen this work twice. One took 25 years, the other took 30 years. I'm not sure anybody wants to wait that long. The other issue is if you are having poor quality water leaving, you're now sending it downstream. So you may have a discharge permit issue, you may have to have treatment. There's some drawbacks here, but bottom line is if you could do it fast enough, often enough, you could keep the bottom water from ever going anoxic and having the problems. Now that takes a run of the river impoundment with a lot of water coming in. It's not going to work on kettle hole ponds or most of the lakes we deal with. Dyes basically prevent light from getting in. No light, no growth. Well, you're not going to turn it black like right where he's pouring the dye, but you could restrict light to some degree. The problem is that's not going to stop all growth. It's going to favor surface scums that get right to the top, and it's a little bit hokey looking. So that doesn't get used a whole lot, but in ornamental ponds or golf course ponds or things like that, it is an option. Dredging. Well, if you can take out the offending sediment, the sediment that's causing recycling of nutrients inside, and that is the dominant source in your lake, and it may not be, you have to look at the watershed and understand where the nutrients are coming from. But if you can take that sediment out and get back down to an infertile base, you can make a huge difference. I mean, you are setting this lake back in geologic time. This is true restoration, although you're pretty much going to destroy the system to do it. It's been likened to burning down the house because you have termites. Well, if the termites are that bad, it might be a good solution if you can collect the insurance money. It does address sediment accumulation. It is ecologically disruptive. You can do sediment dredging in the wet with a hydraulic dredge that pulls it out. The same way as a vacuum cleaner uses air to get out dirt, this would use water mixed with sediment to pump the slurry somewhere and settle it out. So you don't have to drain the lake. And that's what's happening in the lower right. They're doing it hydraulically. But it's expensive. It's hard to permit. And it doesn't have any effect on the watershed inputs. So if your watershed is an issue, dredging's a really expensive way to get some benefits, but it probably won't give you what you want. Phosphorus inactivation. This is turning out to be a remarkably flexible approach. We are adding a chemical to the water. That makes some people unhappy, and I get that. But if you, again, have that boat full of water, you got to get the water out, and this does it. This basically inactivates the phosphorus. You can do it in the water column, or you can do it for the sediment, and it will keep that phosphorus from getting back into the water column. There's different ways to go about it, different types of treatments being done. You can do it with an inlet. You can do it as a low dose treatment in the lake just for the water column, or you can do a higher dose treatment that affects the superficial sediment. The factors in planning phosphorus inactivation are that you need to understand where the load's coming from. If the internal load is at least a quarter of the total, it's worth considering. If the external is overwhelmingly the problem, the stuff coming from the watershed, there's not much sense in doing this because it's not going to last very long. Although you could do it on a maintenance basis by treating an inlet tributary that was a particular problem, and I have projects like that. You need to understand the sources, the inactivation needs. There's a lot of field and lab testing. What types of available sediment are in this, or excuse me, available phosphorus are in the sediment, the system bathymetry, hydrology, the water chemistry, what potentially sensitive receptors there are, because not all the inactivators are totally benign. You can kill fish with aluminum if you don't do it right, and what the accumulated residues are going to be like. So there's a lot to consider. There's different ones to use. Iron's actually the most common natural binder, but it doesn't hold phosphorus when there's low oxygen. So it doesn't help us unless we're also doing an oxygenation system. Aluminum is the most commonly applied binder, certainly in New England. Calcium's been used in some high pH systems. Lanthanum, which is the active phosphorus binder in Phoslock, if you've heard of that product, has been more recently applied. It's had some very good successes. And again, you can use it in the water column or in the sediment. What I'm showing on the bottom here is actually a low dose water column treatment where we're putting in 1 or 2 up to 3 milligrams per liter in these shallow lakes that have had huge phosphorus concentrations in the summer. It has an urban watershed, but it also has high internal loading. We've managed to knock the loading way down, and while it's not perfect, it's a huge improvement. These lakes are way clearer than they used to be. That then lets rooted plants grow, and they wind up having to deal with them. And then when they deal with the rooted plants, they wind up getting algal mats, so it kind of becomes aquatic whack-a-mole. So again, not a perfect solution by itself, but you can get a lot of benefit. It's a great maintenance thing while you're working on the watershed. When you do these treatments, almost invariably, you get a shift away from cyanobacteria. Even if you don't reduce the phosphorus as low as you'd like to go, you're going to shift the ratio of different nutrients. There'll be a higher nitrogen phosphorus ratio, a higher silica to phosphorus ratio, and you will favor other types of algae. Long Pond is on the Cape. You can see that on the left side there, prior to treatment, they had tremendous blue-green blooms. Afterwards, none. Oh, there's still some blue-greens that show up, particularly late in the season, but no blooms. Excellent clarity, usually 5 to 6 meters. It's worked extremely well, and that was a treatment in 2007, so we're 14 years out now. You can also do this for tributary inactivation. I mentioned that before. This is a system in Wellesley, Mass, where we've got a couple tanks with polyaluminum chloride and a pump system in a box to protect it, and it's tributary by precipitation, and basically treats these two major tributaries from about now, I turned it on last week, till 4th of July. And if we can get that far with good quality water, we get through the summer pretty well. As you can see, not just cyanobacteria, but lots of algae were problems beforehand. Since then, it's done extremely well. Okay, oxygenation and circulation could be a subject of a whole course, and this is a hotbed of activity right now. There's a lot going on, a lot being learned. Oxygenation is simply getting more oxygen in the water. Circulation is moving the water around, which will also give you some oxygenation. But as you can see from the diagram, there's a bunch of ways to do this. It's not one technique. So you have to be very careful what you're talking about and be very clear about what you're doing. Oxygenation gives you all the benefits in black. It puts more oxygen in, alters the pH in favorable ways, creates suitable zooplankton refuge, which gives you some more grazing capacity. Circulation can do all that. It also gives you turbulence that often neutralizes the advantages conveyed on buoyant cyanobacteria. They don't like being mixed up and down in the water column, so they often go away. Not always, and there are cyanobacteria that aren't buoyant and may be favored by this. So again, not perfect. The homogenization also gives you consistent water quality, which if you're a water supplier, you're happier with a lower average water quality as long as it's constant because you can treat that. There are 4 major ways to actually put oxygen in the water, so it's a pretty complicated stuff. I will tell you that the dominant ways now in a really deep lake, they simply diffuse oxygen into it in the deep water and the bubbles are absorbed and don't cause destratification. The real wave right now is in side stream supersaturation, which is to pull the water out of the lake, oxygenate it to a supersaturated degree and put it back in where you got it from, and the oxygen spreads out. Nanobubbles are sort of a version of this. I think that the people that do side stream supersaturation and the people who do nanobubbles don't like them being confused or lumped together, but it's the same idea, except you're supposedly making really tiny bubbles that stay in solution until they're absorbed. I have not found it to work very well in the lakes that I was trying to oxygenate the bottom water in, but there's still work to be done. I don't think it's a bad technique. It's a failure of implementation right now. On the other hand, side stream supersaturation, where you pull the water out, oxygenate it, put it back, is a proven technology. It's had some issues over the years in terms of making it work and making it efficient, but it's a pretty good system going on right now. Dr. Paul Ganser sort of perfected it, and he's working with the folks at Vertex to apply it. We've got one out on the Cape right now that's doing very well, I think. Key factors in oxidation, you got to put enough oxygen in to counter the demand. That demand is pretty significant, and it's going to increase when you give it more oxygen. I don't have time to go through all the details of that, but you have to put in more oxygen than you'd think. You got to maintain the oxygen that are suitable for whatever aquatic biota you want to have, or at least keep it above 2 milligrams per liter to keep the sediment chemistry and interactions with the water column where you want. You got to have enough phosphorus binder to bind up that phosphorus. Just because you have oxygen doesn't mean that you'll have enough iron, calcium, aluminum, or lanthanum. You may have to add some. And if you don't want to break stratification, this is the sort of thing you do. On the other hand, if you don't mind breaking up stratification, it's not all that deep a lake, it just stratifies once in a while or doesn't at all, you can use diffused air. You can use a downdraft pump to push water down. That's a Resmic system that's made in Australia, but there's some in the US, or an updraft pump that pulls water from the bottom up. What I'm showing there is the solar bee. They can all work. The problem is you need to move enough water to make a difference. Fountains are also, the same idea. It's an updraft pump. The catch is that often don't size them correctly, and it takes quite a lot. You have to move enough water to prevent thermal gradients from occurring. That way you don't get the oxygen problems. A general guide of 1.3 cubic feet per minute for air systems, but you could need as much as 2 to overcome the sun's heat input. Keep in mind, you're not getting rid of heat, you're just mixing it in the lake. And the warmer the water gets, the more energy it takes to keep it mixed. So it gets pretty darn expensive by the end of the summer. And most people won't build a system that big. They'll just suffer through the last month or two. Unfortunately, that's when the cyanobacteria are at their best. You need to move at least 20% of the target volume per day if you're pumping, and you may need to move 100% per day. When we figure out the volume and figure out what you need for a pump, that's pretty daunting if you're really trying to do the job on a good sized lake. You need to get the oxygen down near the bottom, but you don't want to resuspend the sediment. And you need to move the water into deep zones, like 3 times the Secchi disk, if you actually want to lower the biomass. You will get a shift away from cyanobacteria with most mixing systems, but you won't necessarily get less algae because you haven't put them in the dark long enough. Rough fish regeneration is another thing. If you've got a lot of catfish or carp in the lake, they tend to stir up the bottom. Minimizing them can help. Rooted plant assemblages, technically, if you have lots of rooted plants, you usually don't have too much trouble with algae, but of course, then you may have a rooted plant problem. So people don't go around overplanting their lakes to get rid of algae using rooted plants. Selective nutrient addition is a fascinating area. There's been some really interesting research over this over the last few decades. If you add a lot of nitrate to a lake, you probably will not get a cyanobacteria bloom because it will favor other algae to the point where greens will most likely bloom. But they're still going to bloom. It's still going to be a green lake, and you're probably not going to be happy with it. But if toxicity is the main fear, you can often get rid of it by adding a lot of extra nitrogen. I have never had the guts to tell a client to add nutrients to get rid of a phosphorus problem or get rid of an algae problem. It just seems contrary to everything I was ever involved in. So, but they do it in fertilization, things for production of salmon and such out west. There is solid evidence that this can work, at least in terms of shifting the algae. If you increase the silica availability, you'll prolong the diatom bloom in the spring, which is something that zooplankton can eat. So that could be useful, particularly if you're interested in fish production. Bottom line is, in the end, you have to have a biological structure that favors what you want. You've got to have those zooplankton to eat the algae you produce when you shift them away from the cyanobacteria. And so you really have to know a lot about the biological structure, and biology changes over time. So it's not quite as reliable as a lot of other techniques. Bacterial additives, you know, this could be a very long discussion. The reality is that a lot of the things are proprietary. A lot of it, you don't really know what you're putting in. The best explanation I've heard is from Pat Sims-Geiger of Diversified Waterscapes out west. Use an algicide to kill the algae. You put in something that produces enzymes to break down the long chain hydrocarbons, mostly their cell walls and such. And then you let bacteria metabolize the shorter chain ones and consume them. And you may need oxygen to get that process to go well. And then you use a settling agent to drop out the particulates, including the bacteria. 4-step process. Most bacterial additives are sold as a single product. Well, are they getting all 4 out of that? Not likely. We don't know what's in them. I have seen some wonderful success stories with this. And if you go into the sludge handling industry, they're tested like crazy and adding stuff and manipulating things to minimize sludge. So you know this can work. But we're just dumping a product we buy off the internet into a lake without knowing exactly what it's going to do or how it's going to do it. That's not terribly responsible. So I'm not poo-pooing these. I think they have real merit and some scientific background, but there's really no peer-reviewed science. They don't tell you what's in it. It leaves a lot to be desired in terms of application, at least for professional lake managers who take this stuff seriously. All right, so the roll call, I mean, nothing should be thrown out. That's like at the bottom of the list there. Every tool has a potential purpose. So if somebody tells you why you shouldn't do X, Y, and Z, that means they're probably trying to sell you A, B, and C. Really though, think through the logic for your individual case. Watershed management is always job one. It protects the lake. Unfortunately, it's rarely going to rehabilitate the lake when you've got a cyanobacteria problem. Phosphorus inactivation is incredibly flexible, works very well, but it's not perfect. It doesn't give you everything you need every time. Oxidation also highly desirable. Doesn't seem like there could be a downside. There's a couple possible issues, but for the most part, you're not going to go wrong doing this. You just may not go as right as you would like to go. Circulation, if you can make it deep down, that will work. Circulation in a shallower system is less efficient. It takes more energy, but if you mix that with inactivators, dyes, or even bacterial additives, you may make a big difference. Keep in mind, most of these techniques are not mutually exclusive. And in fact, it'd probably be unusual to solve all your problems with one technique. Dredging, where you're ready for a total ecological overhaul, that's a completely reasonable way to go. If money and permits were an object, I would dredge a lot of lakes, but they're always an object. Algicides with proper timing and limited usage are not an evil thing. They are incredibly helpful when done right. Again, it's a tool. If you use the tool as a weapon, that's a whole lot different. Sonication for susceptible algae, those that will respond to it, and not all do, where you have limited control over the nutrients, that can be helpful. Biomanipulation, if the phosphorus is not too high and you're willing to accept a certain amount of variability, it's the icing on the cake. It often greatly improves your system and gives you some buffering capacity to handle little nutrient pulses, but it usually won't get the job done by itself. And then again, everything else that's been mentioned has a place. They're just somewhat specialized. Just like being a carpenter or a surgeon, you need to pick the right tool for the right job. And that is it.
Okay, Ken, thank you very much. I hope my audio is coming through clear. I'm using a different technique. Ken has my set.
Yeah, you sound fine to me.
Okay, great. All right, well, thank you, Ken. And again, thank you to Hillary for their presentations. We do have a few questions that have come in along the course of the webinar, and I will read through those, and I hope that both you, Ken, and Hillary will chime in with your perspective. The first question came in while Hillary was presenting. I don't know if it's for Hillary, but Ken also does a lot of microscopy work. What magnification is needed for the microscope for identifying cyanobacteria?
Hi, everyone. Well, Ken's the expert in the phycology department, but we usually use a minimum of 400x for looking at level identification.
You can often see what you need to see if you know a lot about algae at only 100 or 200x. But that's after a lot of experience when you're used to it. If you're trying to do this as a volunteer and learn about them, you need to see as much detail as possible. So I would say which is a 20x objective, excuse me, a 40x objective and a 10x ocular. There's other combinations you could use. And I would also say that you want to have phase contrast, not just bright field, if at all possible. But to get a general idea what you have or get a decent picture, that's not essential.
Okay, thank you. The next question is, what is the approximate cost of the Beagle Bioproducts fluorescein monitor?
The fluorometer, the Beagle fluorometer, which Beagle is no longer in business, it's actually made by AmiScience, and it's what we use because we really targeted to kind of go with the most inexpensive instrument that seemed to be pretty reliable. That right now is about a $1,600 instrument, and it does chlorophyll and phycocyanin channels on it. So it's a 2-channel fluorometer.
Okay. The next question is, do the disturbances of water caused by large motor boats, especially wake boats, particularly to the bottom of the shallow lakes, contribute to cyanobacteria disturbances, including blooms during the warm summer months when boat activity is at its peak? Should this be a consideration in managing such wave generating boats on some water bodies?
Okay, there's a bunch of different things embodied in that. The short answer is, of course, it's possibly an influence, but it pales in comparison with what the wind can do or what people do on shore that adds nutrients to the lake. If you want to chase down wake boats or any other watercraft as being somehow detrimental, look in the mirror first. In a shallow area, certainly they can resuspend sediments, and some of that may become available to algae. I don't think that they have a particular bent that would make them favor cyanobacteria over any other type of algae. But yeah, they're going to make more turbidity. They're going to potentially let greater algae grow. They're probably not likely to be the trigger for cyanobacteria blooms, but it is true that the turbidity increases. Oftentimes that could trigger the cyanobacteria growing on the bottom to want to rise. So there's a lot of possible ways there, but I don't think you could stand up in a meeting and say, these things are the cause of our blue-green algae problems. That's pretty unlikely.
Okay, thanks, Ken. What evidence has documented the adverse effects of wake boat activity on the evolution of cyanobacteria blooms in a given lake? It's kind of building on the other one. Different person asking the question though.
Yeah, I'm not aware of them. Again, they're tremendous amount of influence on the shoreline in terms of possible erosion and damage there. They could resuspend stuff from the bottom. I think I saw that Danielle Wayne is on here from the Seven Lakes Alliance up in Maine, and she's done quite a bit of work on this too. Once you're below about 15 feet, there's not that much influence on the bottom. The issue is laterally going out on the shore. In really shallow zones, frankly, there should be regulations to minimize the creation of wake in those shallow zones for all sorts of reasons, not just cyanobacteria.
All right, thank you. In urban systems, what are your thoughts on daylighting stormwater systems in order to allow for terrestrial plants to absorb some of the phosphorus from the stormwater runoff before reaching the water body?
I think the daylighting streams is never a bad idea ecologically. But again, the idea that you could get enough removal in a stream on its way to the lake is from an urban area is pretty unlikely. Again, they just overwhelm any best management practice we have. If you look at the EPA's database, which is quite nice on stormwater management things, about the best you ever do is a 50% removal. But when you urbanize an area, you bump up the phosphorus inputs by an order of magnitude. So if you make them up by tenfold and you cut them in half, it's still a fivefold increase. There's a lot of other things you can do. There's things you can put in stream channels now to absorb phosphorus as it comes through. I know CPRO's selling a new one, and there's other ones that are out there that absorb phosphorus, and absolutely nothing wrong with encouraging more uptake by plants. But I don't see that as being able to prevent nutrients from getting into a lake at a potentially alarming amount from an urban or agricultural watershed.
Okay, thank you. If given a choice between microscopic versus fluorometric data, is microscopy always better if available?
Well, it depends on what you're trying to do with it. I can leave that to Hillary, but as a first cut, I think the fluorometric data is going to give you a lot more data, a lot faster, of a lot more area, and you can do more with it. You follow it up with microscopy. Hillary, what do you think?
Yeah, I agree exactly with that, Ken. I think it helps calibrate the instrument. So you may need microscopy, look at cell counts and kind of calibrate the instrument for the fluorescence. But yeah, the tool is great. It's reliable. It's simple to use, and it's timely. I mean, you can get those readings at the same day. So I'm a high advocate of it.
Yeah, if you have a flow cam or cyber system that actually does the counting for you and can help you with identification, that can be useful. Those go for $90,000 and up, a bit more than the $1,600 for the fluorometric device. And of course, the amount of expertise to really know what you're looking at, it takes a lot of time. And there's really only a few dozen people like me that look at algae for a living. And I don't even do it full time. And some of the best people out there, Ann St. Amand, Andy Chapman, and these people do this routine, but they can't handle the volume that comes through. We have to use surrogates, and the fluorometry is a really good one.
And if you're looking for an investment for the cost it takes and the time involved, it is a really nice tool.
All right. Our next question is, should we be looking for benthic cyanobacteria mats in our lake? We've recently experienced surface blooms.
That's a very good question. I think the answer is yes, whether you had a surface bloom or not. I got called in to look at taste and odor issues in a water supply reservoir in Connecticut, and they had no blooms in the water column at all. We finally put a camera down and looked underneath and went, yo, look at all the blue-green mats on the bottom. And that's where the taste and odor was coming from. And they could be emitting toxins as well. So knowing what's on the bottom is important. Now, it's not going to be real deep down where there's no light. There has to be light. But out to 15, 20 feet, absolutely. Check that out, because that could be a significant source. Elizabeth Hilborn gave a nice slide in her presentation to the last webinar showing how you could actually have toxic events even though the water looked just fine.
Yeah.
Okay, this one came into me by email last night, so it's a bit of a buildup. But there was some conversation at a lake association about holding off on swimming and notifications if there isn't an obvious scum on the lake. So the questions are, and there are a few of them, if a bloom is in fact toxic, how long will meaningful concentrations of toxicity linger in the water?
You said if it is toxic?
One at a time.
Yeah, I mean, they're usually gone in a fairly short amount of time, maybe 3 days, but there are some that can persist and stay quite a while. I'm a big proponent of actually doing toxicity testing because just seeing the algae doesn't actually tell you that there's anything there. Even seeing an alga in the microscope that I know is a potential toxin former, there's no guarantee. The data that are out there suggest that it's about a 1 in 5 chance of toxicity if you've got a pea soup green lake. You don't know. Now, do you want to take that 1 in 5 chance and swim it or drink that water? I don't think so. And you'd sure let the people know the risk, but it's not a guarantee that you have toxicity unless you test for it.
Right. And just to add to what Ken's saying, those like cylindrous spermopsin, which can persist for a couple of weeks after a bloom event. So it might like look perfectly benign and fine, and you can still have those toxins present in extracellular conditions. So.
All right. The other part of it is there any realistic way to tell people to hold off on swimming when there's nothing to see? And the examples are they may only have that weekend at the lake, then they're gone. So they may be missing out on swimming. And then the individual who asked the question said, sometimes when I'm hanging over the end of my dock to read my water level gauge, I can see many little green specks in the water column that I'm sure are cyanobacteria, but are nowhere near being a bloom. I'd miss out on a lot of swimming if I let these little specks scare me off.
Yeah, that is actually a great layout of the question, very astute observation. I can only echo what Ingrid Koros, who just retired, she was like the German expert on this stuff, and she was in the Cyanobacteria Monitoring Collaborative Conference that Hillary and folks put together earlier this year. And she said, look, you get people that are going out for their vacation, they get there, and you're going to see posted signs warning them of toxicity and everything else. And they look at the lake and it looks fine. I mean, come on. Her point, and Hillary made it again today, it's about dose and exposure. I'd be worried about kids consuming that water because they do tend to swallow a lot of it. But as a person, as an adult, to go out and swim across that lake, if it wasn't really abundant, it wouldn't bother me any. The risk is low. Is there a risk? Of course. You have to trade it up. And her point was in Germany, a lot of these people go out and have their little cottages by lakes, and you can't tell them. You can, and frankly, I don't think when we post lakes, we may close public beaches and such, but you don't actually have a legal authority in most places to say, sorry, you can't touch this water. So it's a challenge. I think people have to decide risk for themselves. After all, I mean, most people didn't get in a car to come to this presentation. This is pretty nice technology, but it used to be when we'd get together, everybody drove there. You know you could get killed in a car accident, but you thought it was worth it. You kind of have to play the same game with the lakes.
Yeah. And the other thing I'll add to that too is monitoring strategies. Things like fluorometry, again, you could use that as a tool to look at what that potential risk might be and identification of what those green specks are in the water column. And then you can make that decision for yourself. You're a hypersensitive individual or not might add to how you perceive that potential risk. But
that's a real good point. And keep in mind that they're finding now that we actually have airborne toxins. So just sitting by the lake and not touching it may still be a risk.
Right.
Okay, are you guys good on time? We have a couple more questions that we can get through if you're okay on time.
Sure.
Sure.
Okay. Do you have any suggestions for background literature relating to the presence and concentration of cyanotoxins in scum versus subsurface samples during a planktonic bloom? We are having some resistance to collecting scums during a harmful algal bloom response, and collections are being retrieved below the scum.
That kind of defeats the purpose. If your objective is to look at maximum risk from a public health standpoint. So that's kind of interesting to me, but I don't know how you feel on that, Ken, but.
Well, there are some, the question about references, there's a 3-paper sequence in Lake and Reservoir Management from 2009, I believe, September issue. One looking at the distribution of microsystems in Minnesota, one for Missouri, and one for Florida. And they did look at what happens when you take a sample out in the middle of the lake where it's pretty well mixed versus coves and shoreline. And sure enough, as we kind of all know today, it's those high concentration areas that make the greatest risk. That 20% probability of toxins is from those scums. You go out in the middle, it became a 1% probability because you weren't sampling the right stuff. And of course, people are using the whole lake, but probably a lot more are using the shoreline where those scums develop. So I think Hillary's right. You've got to get, if you're worried about true risk, you have to get at the highest concentration.
Okay, Hillary, this one is for you. I'm a lake manager who works in the southeast on Lake Marion and Lake Moultrie. Is the Cyanobacteria Monitoring Collaborative program exclusive to lakes in the northeast?
The program is made to be used by whoever is interested in using it. I mean, us going there, where did they say they're located again, Amy?
In the southeast. They
Okay.
didn't say what state, but it's Lakes Marion and Lake Moultrie. I'm not sure where those are.
It's Georgia or South Carolina. Yeah.
Okay, thanks, Ken, because I didn't know that. And no, this program we designed to really be a tool useful to whoever wanted to participate and take it. So like you saw, gave my presentation, the tools are globally available. The kits are available to anybody that wants to. We have a quality assurance project plan that lists out the steps that anybody can grab and utilize to start their own program or collaborate with us. So yeah, it's open. We have participants all across the country.
Okay, we have 3 more. Are there any ways to estimate toxin concentrations using fluorometry?
Yeah, not really.
The short answer is no. There is a paper that Jim Haney was involved with that suggests some equations that based on the level, you might have some correlation to it, but it wasn't reliable enough for me to suggest anybody believe that for their given lake. I think it was work on 2 or 4 lakes. You'd need to do a whole lot more, but you can't look at the algae and know if they're toxic. You can't look at a feature of them like fluorometry and know. You really have to measure the toxins.
But if you start combining those tools together, like, you know, over time,
True.
you get a pretty good picture. Yeah. So
Again, everything needs to be thought of as probabilities, not yes and no.
Okay. The next one is when we use copper to treat cyanobacteria, how long does the copper stay in the water? And how serious are corrosion concerns over time?
It only stays in the water for hours, not days. Oftentimes it's pretty well inactivated and on its way settling out in minutes. You know, if it's right by an intake of some kind, it could be an issue, but people have had, lakes have been subjected to copper treatments in places for 50+ years, and they've measured it in the sediment. To the best of my knowledge, no one has ever found a problem with it once it gets in the sediment. It can't be good, but it does not appear to be measurably bad.
All right. And what good methods are there for reducing Lyngbia mats?
That's one of the hardest ones to do. It kind of goes hand in hand with green algal mats as well. You have to prevent it. Once the mat has formed, it is very difficult to get rid of. So, for example, if you use sonication in an area, you could prevent the mat from forming. If you did a preemptive algicide treatment when things are just starting to get going, you can prevent it from forming. But once you see that you have mats, I don't know of anything that will truly get rid of them. Some people have had some pretty good results with flumioxazin, which is the active ingredient of an herbicide called Clipper. But mostly once the mat is really thick, you're just burning or killing the outside of it and you're not getting at the inside. It really needs to be about prevention, not getting rid of it.
Okay, and I'm going to slip one last one in there. Why do you want to avoid mixing of layers in a stratified lake? Wouldn't that help raise the low oxygen in the bottom?
It would. Unfortunately, it would kill your trout if you were having trout live there. Of course, if there was no oxygen, that wouldn't be a problem. But it's the natural state of the lake is stratified in the summer. And changing that natural state may have a lot of other unintended consequences. It's going to warm the water as well as add oxygen, so it may not support a cold water fishery. It may change things with regard to the way the zooplankton function and how they migrate. There's a lot of other reasons. And frankly, that's a permitting question when you go into, it's like, why are you destratifying this lake? There may be, if it's a water supply, they often want those layers separate so they can draw from one or the other. So there are a lot of possible reasons. It is not impossible to do it. It's not always a bad idea. It's just in many cases, you're not supposed to do it.
All right, that is all I see. I'd like to thank both of you gentlemen, Hillary Snook and Dr. Ken Wagner, for your presentations. So everyone knows this has been recorded, and we will be sharing the links off the NECNOM's website, and then also the link will be emailed out to everyone. So thank you for joining us today, and have a good day.
All right, take care.
Thank you all. Bye-bye.